The steam valve closes with a metallic wheeze, cutting pressure to the cylinder. Inside the crane cab, 40 feet above the harbor floor, the operator's hand moves methodically across the controls. He sets the drum brake. Cast iron shoes grip the steel wheel with a low groan. The ratchet pawl drops into place. The hook hangs 60 feet down, carrying nothing, swaying slightly in the draft that rises through the warehouse door. It is 11:30 at night. The last cargo nets came off the Adelaide 2 hours ago. The boiler in the engine house will be banked until morning, pressure dropping to standby. The crane, a 70-ton overhead gantry built in 1891, sits in mechanical stillness. Its counterweight, 18,000 pounds of iron plates stacked in a steel cage, hangs motionless on the opposite side of the drum. The system is balanced, or near enough. Hook and chain weigh slightly less than the counterweight, but friction in the drum bearings and the brake hold everything in place. The operator climbs down the iron ladder. His boots ring on the steel rungs. He walks across the warehouse floor, past stacked crates of machine parts and sacks of grain. The night watchman nods to him from the side door. Outside, the harbor is quiet. A single electric arc lamp buzzes on the pier. The water is black and still. Inside the crane, nothing should move. The drum is locked. Chain hangs in a vertical line, each link resting against the next under its own weight. The hook at the bottom, a forged steel piece weighing 200 pounds, points downward. The counterweight on the other side of the drum sits in its frame, compressed slightly by gravity against the bottom stops. Everything is static, but in the hours after shutdown, small forces remain. The steam cylinder still holds residual pressure, not enough to move the piston, but enough to exert a gentle bias against the seals. The brake shoes, hot from the day's work, begin to cool unevenly. The chain, stretched slightly during lifting, begins to contract as the metal cools. The counterweight frame, heated by friction during operation, cools more slowly than the hook chain exposed to the night air. Thermal differentials produce microscopic shifts in length, tension, and balance. At 2 in the morning, the brake shoes tick. A faint sound, like a settling timber. The drum does not turn, but the brake's grip shifts fractionally as the metal contracts. The chain sags by a quarter inch, then stops. The hook remains where it is. The counterweight does not move. Silence returns. At 4 in the morning, the cylinder pressure equalizes slowly through a valve that doesn't seat perfectly. The piston shifts backward by a 1/16 of an inch. The force transmitted through the linkage to the drum is negligible, but it is present. The brake holds. The drum does not turn. But the balance has changed. The soundscape is minimal, the slow tick of cooling metal, the faint creak of the chain under load, the distant sound of water lapping against the pier pilings. The crane sits in darkness. The hook hangs. The counterweight waits. And in the hours before dawn, something begins. The morning crew arrives at 6. The boiler is fired. Steam pressure builds slowly, gauges climbing toward operating range. The crane operator climbs the ladder to the cab, carrying a tin cup of coffee. He sets the brake release lever, but does not touch the throttle yet. He looks down at the hook. It is higher than it should be, not by much, perhaps 6 inches. But the operator knows where the hook hangs at rest. He has worked this crane for 3 years. When the crane is idle overnight, the hook settles to a specific height, low enough that the bottom is 8 feet above the floor. This morning it is closer to 9. He climbs down and walks to the chain. He looks up along its length, following the line to the drum. The chain is taut. There is no slack, no kink, no fouling. He touches one of the links. It is cold. He looks at the floor beneath the hook. Yesterday, someone spilled lubricating oil near the base of the chain. The oil stain is still there, but the hook's shadow has shifted. It no longer aligns with the mark. He calls the shift foreman. The foreman brings a piece of chalk and marks the warehouse wall at the height of the hook's lower point. He measures the distance from the floor with a folding rule, 8 feet, 7 inches. He checks the logbook. The last entry from the previous night's operator notes the hook at 8 feet, 1 inch, 6 inches of movement, with no steam, no power, and the brake set. The foreman inspects the brake. The shoes are seated firmly against the drum. He checks the ratchet pawl. It is engaged. He examines the counterweight. It hangs in its frame, resting on the lower stops. There is no visible damage, no broken cable, no slipped pulley. He tests the drum by hand. It does not turn. They operate the crane normally throughout the day. Loads are lifted, swung, and lowered. The hook moves up and down as expected. The brake holds under load. Counterweight rises and falls in its frame. At the end of the shift, the operator lowers the hook to 8 feet 1 inch, matching the previous night's log entry, and marks the wall again with chalk. He sets the brake. He closes the steam valve. He climbs down. The next morning, the hook is at 8 feet 8 inches, 7 inches higher. The foreman measures it twice. He compares the new mark to the previous one. The hook has risen again overnight. He looks at the chain, the drum, the brake, the counterweight. Nothing is visibly wrong. He writes in the log, "Hook elevated during shutdown, cause unknown." That night, he stations a watchman inside the warehouse with instructions to observe the crane every hour. The watchman walks the floor with a lantern. At midnight, the hook is at 8 feet 8 inches. At 2 in the morning, it is at 8 feet 9 inches. At 4, it is at 8 feet 11 inches. By 6, when the morning crew arrives, it is at 9 feet 2 inches. The hook is rising. Slowly, steadily, without power. The chain is lifting itself. By the end of the first week, the pattern is undeniable. Every night after the steam is shut off and the brake is set, the hook rises. The distance varies, some nights 4 inches, some nights 10, but the direction is always the same. Up, the crew begins tracking it systematically. Each evening, the operator lowers the hook to a standard height and marks the wall. Each morning, the new height is measured and recorded. The logbook fills with entries, +6 inches, +9 inches, +5 inches. The movement is not constant. Some nights show more lift than others. But over 2 weeks, the cumulative rise is more than 8 feet. The soundscape changes. During the day, the crane operates normally, the hiss of steam, the clank of the drum, the rattle of the chain. But at night, in the hours after shutdown, new sounds emerge. A faint creak from the drum housing, a slow, irregular ticking from the brake assembly, a metallic whisper as the chain shifts link by link through the sheave blocks. The night watchman reports hearing the sounds, but seeing no movement when he shines his lantern on the hook. The motion is too slow to observe directly. But when he returns an hour later, the chalk mark has moved. The crew begins to notice other changes. The chain tension feels different in the morning. When the operator releases the brake to begin the day's work, there is a slight jolt, as if the chain were under more load than expected. The drum turns more freely in the upward direction, as though something is assisting the lift. The counterweight, when inspected, shows no obvious change, but the foreman notices that the frame's lower stops are less compressed in the morning than they are at the end of the day. Measurements confirm it. The counterweight is sitting slightly higher in its frame after a night of shutdown. Not by much, perhaps half an inch, but consistently. The counterweight is rising along with the hook. The entire system is shifting upward, against gravity, without power. The escalation is measurable. The foreman installs a fixed pointer on the warehouse wall, aligned with a specific link in the chain when the hook is at rest. Each morning, the link has moved upward relative to the pointer. He photographs the chain at shutdown and again at startup. The photographs, when compared, show a clear vertical displacement. The evidence is objective. The crane is lifting itself. Theories begin to circulate among the crew. Some suggest the brake is slipping, but tests show the brake holds under far greater loads than the static weight of the hook. Others propose thermal expansion in the chain, but the chain is cooling at night, not heating. It should contract, not extend. A machinist suggests the drum bearings are seizing, but the drum spins freely during operation. The boiler engineer wonders if residual steam pressure is involved, but the cylinder is vented and the piston shows no movement. One night, the foreman stays late and watches the crane from the floor. He sits on a crate, smoking a pipe, listening. The warehouse is dark except for a single oil lamp on a post. He hears the ticking. It is irregular, spaced minutes apart. He hears the creak of the chain. It is faint, almost inaudible but persistent. He watches the hook. It does not move visibly. But when he closes his eyes and listens, he can sense it. A slow, patient tension, as if the crane is pulling itself upward 1/fraction of an inch at a time. By the end of the third week, the hook has risen 12 feet total. The crew lowers it back to the starting height each evening, but each morning it is higher. The crane is not haunted. It is not broken. It is obeying some principle the crew does not yet understand. The port authority sends an inspector. He arrives on a Tuesday morning with a clipboard and a set of calipers. He examines the brake shoes, measures the drum diameter, checks the chain for stretch, and inspects the counterweight for hidden weights or tampering. He finds nothing irregular. The brake is functioning. The chain is within tolerance. The counterweight matches its documented mass. He watches the crane operate for 2 hours. It performs normally. He writes a report concluding that the overnight movement is likely due to operator error in setting the brake or recording the measurements. The crew disagrees. They demonstrate the phenomenon. The inspector is invited to stay overnight. He marks the hook position himself at shutdown and measures it again at dawn. The hook has risen 8 inches. He rechecks his measurements. They are accurate. He revises his report. Cause unknown. Recommend mechanical investigation. Sabotage is considered. The warehouse is locked at night, but the building is old, and there are gaps in the walls. Could someone be entering after hours and manually lifting the hook? The foreman stations 2 watchmen inside, one at each end of the building. They patrol in shifts, crossing paths every 30 minutes. No one enters. No one touches the crane. The hook rises anyway. Faulty brakes remain the leading theory. A specialist from the crane manufacturer is brought in. Disassembles the brake, inspects the shoes, measures the spring tension, and tests the friction coefficient of the braking surfaces. He finds wear consistent with years of use but no defects. He reassembles the brake and observes it overnight. The brake does not slip under static load. He applies a torque gauge to the drum. The brake holds against forces far exceeding the weight difference between the hook and counterweight. He concludes the brake is not the cause. Operator error is revisited. Could the evening operator be inadvertently leaving the brake partially released? The port authority assigns a different operator to the evening shift. The new operator is meticulous. He sets the brake, tests it manually, and verifies the drum is locked before leaving. The hook rises overnight. The morning operator, suspecting the evening operator of sabotage, swaps shifts with him for a week. The phenomenon continues regardless of who sets the brake. A theory emerges involving uneven counterweight loading. Perhaps the iron plates in the counterweight cage have shifted, changing the balance. The counterweight is lowered to the floor and disassembled. Each plate is weighed individually. The total mass is confirmed, 18,000 pounds, matching the design specification. The plates are restacked in the same configuration, and the cage is reassembled. The crane is tested. The hook still rises overnight. The crew begins to suspect the chain itself. Perhaps the chain is somehow creeping upward due to vibration or resonance. But the warehouse is isolated from rail traffic and heavy machinery. There is no significant vibration source at night. A seismometer is installed on the floor near the crane base. It records no unusual activity. The chain is not being shaken loose. One evening, the foreman tries leaving the crane under partial steam pressure overnight. The boiler is kept at low fire, and the cylinder is left slightly pressurized. The next morning, the hook has risen 14 inches, more than on any previous night. The experiment is repeated with the cylinder fully vented. The rise is 6 inches, closer to the average. The correlation is noted. More residual steam pressure corresponds to more overnight lift. But even with no pressure, the lift still occurs. The crew is baffled. Every mechanical component has been inspected, tested, and cleared. No external interference has been detected. The brake works. The chain is sound. The counterweight is correct. Yet every night the crane lifts its own hook. The behavior is repeatable, measurable, and unexplained. The foreman writes to the manufacturer, describing the phenomenon in detail. The reply arrives 2 weeks later. It suggests checking for brake slippage, counterweight imbalance, or chain stretch, all of which have already been ruled out. The letter concludes with a note. If all mechanical factors are eliminated, consider environmental influences such as temperature variation and pressure retention. It is the first hint toward the truth. The foreman begins tracking environmental conditions. He installs a thermometer on the crane frame and records the temperature at shutdown and startup. He notes that the warehouse cools significantly overnight, often by 20 degrees Fahrenheit or more. He measures the chain temperature at shutdown, 98 degrees, warmed by friction and proximity to the steam cylinder. By morning, the chain is 62 degrees, matching the ambient air. The counterweight, however, cools more slowly. At shutdown, its surface temperature is 85 degrees. By morning, it is still 72 degrees. The thermal mass of 18,000 pounds of iron resists cooling. He considers what this means. The chain contracts as it cools. Steel shrinks by approximately 6/millionths of an inch per degree Fahrenheit. 100-foot length of chain cooling by 30 degrees contracts by roughly 1/5 of an inch. That should lower the hook, not raise it. But the counterweight, cooling more slowly, contracts less. If the counterweight's supporting cable, also steel, contracts less than the hook chain, the balance shifts. The slower cooling counterweight effectively becomes lighter in relative terms, creating an upward bias on the hook side. But the math does not fully account for the observed movement. 1/5 of an inch is not 8 inches. Something else is amplifying the effect. The foreman examines the brake more closely. He notes that the brake shoes are warm at shutdown, heated by friction from the day's work. By morning, they are cool. As they cool, they contract. The contraction is uneven. The outer surface of the brake shoe cools faster than the inner surface pressed against the drum. This creates a thermal gradient that slightly changes the shape of the brake shoe. The shoe's grip on the drum weakens fractionally as it cools. Not enough to allow free rotation, but enough to reduce the static friction holding the drum in place. He tests this by measuring the torque required to turn the drum at different temperatures. When the brake is warm, the breakaway torque, the force needed to overcome static friction, is higher. When the brake is cool, the breakaway torque is lower. The difference is small but measurable. The brake exhibits hysteresis. It grips more firmly when warm than when cool. This suggests a mechanism. As the brake cools overnight, its grip weakens slightly. The drum, held in place by friction, becomes easier to turn. Any small force capable of producing torque can now cause incremental motion. The forces do not need to be large, just persistent and directional. He examines the steam cylinder. Even after the steam valve is closed, the cylinder retains pressure. The piston seals are leather, not perfectly airtight. Over hours, the pressure equalizes slowly through microscopic leaks. But during that equalization, the piston exerts a gentle, sustained force on the connecting rod. The connecting rod is linked to the drum. The force is in the direction that assists upward motion of the hook. It is not enough to overcome the brake when the brake is at full grip. But as the brake cools and its grip weakens, the residual pressure becomes sufficient to produce motion. He measures the cylinder pressure overnight. At shutdown, with the valve closed, the pressure is 12 pounds per square inch. At midnight, it is 9. At 3 in the morning, it is 4. By 6, it is 1. The pressure decays slowly, but during the decay, it exerts a continuous bias. He also examines the counterweight frame. The frame is suspended by steel cables that pass over sheaves and connect to the drum opposite the hook chain. As the counterweight cools, the cables contract. But the counterweight itself, with its greater thermal mass, cools more slowly than the cables. This creates a mismatch. The cables try to shorten, pulling the drum in one direction, while the counterweight's slower cooling resists the pull. The result is a net torque on the drum favoring upward motion of the hook. Finally, he considers the gravitational bias. The system is designed to be nearly balanced, but not perfectly so. The hook and chain weigh slightly less than the counterweight. The difference is intentional. It makes the crane easier to control under load. But in a near-balanced system, even tiny forces can produce measurable effects. If the counterweight side has a slight advantage, and the brake's grip weakens, and residual steam pressure provides a nudge, the system will drift in the direction of the imbalance. He assembles the clues. Residual steam pressure providing a directional force. Brake hysteresis, reducing static friction as the metal cools. Thermal contraction creating differential tension in the chain and cables. Counterweight cooling lag shifting the balance point, and underlying it all, a gravitational bias favoring upward motion when friction is reduced. Each factor alone is insufficient. Together, they produce the effect. The crane is not lifting itself by magic. It is responding to a confluence of small, persistent forces acting over hours in a mechanically biased system. The Port Authority brings in a consulting engineer from the Technical University. He arrives with precision instruments, a strain gauge, a pressure transducer, a set of micrometers, and a portable recording device that traces mechanical deflections over time. He spends 2 days installing sensors on the crane. The strain gauge is clamped to a section of the hook chain. The pressure transducer is fitted to the steam cylinder. A deflection recorder is mounted on the drum housing to track rotational movement. A thermometer array is placed on the brake shoes, the counterweight, and the chain at multiple points. He runs the crane through a full operating cycle, recording data. He shuts it down at the end of the day and begins the overnight monitoring session. The crew gathers in the warehouse to observe. The engineer sits at a makeshift desk with his instruments, noting readings every 15 minutes. At shutdown, the system is in the following state. Steam pressure in the cylinder is 11 pounds per square inch. Brake shoe temperature is 102 degrees Fahrenheit. Chain temperature is 96 degrees. Counterweight surface temperature is 86 degrees. The strain gauge shows the chain under tensile load of 4,200 pounds, close to the expected value for the static weight of the hook and chain. Over the first hour, the pressure in the cylinder drops to 9 pounds. The brake shoes cool to 94 degrees. The chain cools to 88 degrees. The counterweight cools to 84 degrees. The strain gauge reading increases to 4,220 pounds. The chain is under slightly more tension. The drum has not rotated measurably. By the second hour, the pressure is 7 pounds. Brake shoes, 87 degrees. Chain, 80 degrees. Counterweight, 82 degrees. Strain gauge, 4,250 pounds. The deflection recorder shows a movement of 1/16 of an inch in the direction of upward hook motion. By the fourth hour, the pressure is 3 pounds. Brake shoes, 74 degrees. Chain, 68 degrees. Counterweight, 76 degrees. Strain gauge, 4,300 pounds. Deflection, 1/8 of an inch. By 6 in the morning, the pressure is 1 pound. Brake shoes, 64 degrees. Chain, 61 degrees. Counterweight, 70 degrees. Strain gauge, 4,400 pounds. Deflection, 5/8 of an inch. The hook has risen measurably. The engineer plots the data. He identifies correlations. As the brake cools, the breakaway torque decreases. As the cylinder pressure decays, a persistent force is applied. As the chain cools faster than the counterweight, differential contraction creates a tension imbalance. The system, poised near equilibrium, shifts incrementally toward the upward direction. The motion is not continuous. It occurs in small steps, each triggered when the accumulated forces exceed the reduced static friction of the cooling brake. He calculates the net force. The residual steam pressure on the piston, transmitted through the linkage, produces approximately 80 pounds of force on the drum. The differential thermal contraction between the chain and the counterweight cables produces an additional 20 pounds. The counterweight's slight gravitational advantage, due to its greater mass and the near-balanced design, adds 15 pounds. The total is 115 pounds acting in the direction of upward hook motion. Against this, the brake provides static friction. When warm, the brake can resist 2,000 pounds of torque, but as it cools, thermal contraction and shape change reduce the friction coefficient. By the coolest point of the night, the brake can resist only 1,500 pounds. The 115 pounds of net force is insufficient to overcome this, until the brake exhibits stick-slip behavior. Stick-slip is a phenomenon in friction systems where static friction alternates with kinetic friction. The drum is held by static friction. As force builds, the drum remains stationary. When the force exceeds the static threshold, the drum slips suddenly, a microscopic rotation. The motion reduces the friction temporarily to kinetic levels, which are lower. The drum moves a small distance before static friction re-engages. The process repeats. The engineer describes it. Imagine pushing a heavy crate across a rough floor. You push steadily. The crate doesn't move. You push harder. Suddenly, it jerks forward an inch and stops. You push again. Another jerk. That is stick-slip. The crane drum is doing the same thing, except the push is the combination of residual steam pressure, thermal bias, and gravitational imbalance, and the jerk is a fraction of a degree of rotation. He measures the drum's circumference, 10 feet. A rotation of 1 degree moves the chain by approximately 1/3 of an inch. Over 8 hours, if the drum slips once every 10 minutes, the cumulative motion is 16 slips, or about 5 inches. The observed rise is 6 to 8 inches per night, depending on conditions. The math aligns. He runs the experiment a second night with the cylinder fully vented at shutdown, eliminating residual pressure. The hook rises 4 inches, less than average, but still present. The thermal and gravitational factors alone are sufficient to produce some lift. He runs a third night with the brake preheated using steam jackets to slow its cooling. The hook rises only 2 inches. The brake's cooling rate is a critical factor. The conclusion is clear. The crane lifts itself due to a combination of residual steam pressure, thermal contraction asymmetry, brake hysteresis, and gravitational bias, all acting in a system close to mechanical equilibrium. Each factor is small. Together, they are sufficient. The final report is written on a cold morning in late November. The consulting engineer presents his findings to the port authority, the crane manufacturer's representative, and the warehouse crew. He stands beside the crane, gesturing to its components as he explains. The crane operates during the day in a state of dynamic balance. The hook lifts loads, the counterweight descends, the drum rotates, the brake engages and releases. Steam pressure drives the system. At shutdown, the system should be static. The brake locks the drum. The hook hangs. The counterweight rests. But the system is not perfectly static. Small forces persist, and the mechanical equilibrium is delicate. He points to the steam cylinder. After the valve closes, pressure remains trapped. The piston seals are leather. They allow slow leakage. Over hours, the pressure equalizes through the seals and the clearance gaps. But during that time, the piston exerts a sustained force. The force is transmitted through the connecting rod to the crank arm and then to the drum. The direction of the force is determined by the piston's position at shutdown. In this crane, the geometry is such that residual pressure biases the drum toward upward motion of the hook. He walks to the brake. The brake shoes are cast iron, fitted tightly against the drum. During operation, friction generates heat. At shutdown, the shoes are warm, often over 100 degrees Fahrenheit. As they cool overnight, the metal contracts. The contraction is not uniform. The outer face cools faster than the inner face. This creates a thermal gradient that slightly changes the shoe's shape. The grip on the drum weakens. Not enough to allow free rotation under normal conditions, but enough to lower the threshold for stick-slip behavior. He gestures to the chain. The chain cools rapidly because it is exposed to air on all sides. Steel contracts as it cools. Over 100-foot length, a 30-degree temperature drop produces a contraction of approximately 1/5 of an inch. This should lower the hook, but the counterweight, with far greater thermal mass, cools more slowly. Its supporting cables also cool, but not as quickly as the chain. The differential cooling creates a tension imbalance. The chain tries to shorten, pulling the hook down. The counterweight cables try to shorten, pulling the drum in the opposite direction. The counterweight's slower cooling gives it a mechanical advantage. He points to the counterweight frame. The counterweight itself weighs slightly more than the hook and chain. This is intentional. It makes the crane easier to control. But the imbalance is small, only a few percent. In a system with strong friction, this imbalance is negligible. But when friction is reduced, by cooling brakes, by stick-slip behavior, the imbalance becomes significant. The counterweight side has a gravitational advantage. The system drifts in the direction of that advantage. He brings the factors together. Imagine the crane at midnight. The brake has cooled. Its grip is reduced. The cylinder still holds 4 pounds of residual pressure, pushing gently on the piston. The chain has contracted from cooling, but the counterweight's cables have contracted less. The counterweight's gravitational bias pulls the drum in the direction of upward hook motion. The brake resists, but barely. The accumulated forces exceed the static friction threshold. The drum slips, a tiny rotation, perhaps 1/10 of a degree. The chain lifts by a fraction of an inch. Static friction re-engages. The drum stops. He continues. 10 minutes later, the process repeats. The forces have rebuilt. The brake slips again. Another tiny lift. Over 8 hours, this happens dozens of times. Each slip is imperceptible. But cumulatively, the hook rises 6, 8, 10 inches. The crew sees the result, but not the process. The motion is too slow, too incremental, but it is real, and it is mechanical. The manufacturer's representative asks about corrective measures. The engineer nods. Vent the cylinder completely at shutdown to eliminate residual pressure. Install a secondary locking pin on the drum to prevent stick slip. Use a brake design with more stable friction characteristics across temperature ranges. Or simply accept the phenomenon as harmless and lower the hook to a safe height each evening. The Port Authority chooses the simplest solution. A steel pin is installed through the drum housing, locking the drum mechanically at shutdown. The first night after installation, the hook does not rise. The second night, the same. The phenomenon is eliminated, but the crew now understands it. The crane was not possessed. It was not broken. It was simply obeying the quiet, persistent logic of physics. Residual pressure, thermal drift, friction hysteresis, gravitational bias, all converging in a system balanced on the edge of equilibrium. The logbook's final entry on the matter is brief. Cause identified, pin installed, crane operates normally. The soundscape at night returns to silence. No more ticking, no more creaking. The chain hangs still. The hook no longer rises. But for those who witnessed it, the memory remains. A machine, shut down and locked, lifting itself inch by inch through the darkness, driven by forces too small to see but too persistent to ignore.